Hi, I'm Dr. Justin Estry. This is Paul 280 Research Methods, and today we're going to revisit the issue of descriptive statistics. We've done a little bit of this before, just getting some very, very basic ideas to get started with R. Now we're going to go a little deeper into this topic, continuing, of course, to use R. All the code and data necessary to run this, to go through these examples, is available on the course RStudio website if you're following along with the class at Wake Forest. If you're somewhere else, the code and data will be available on the website. So let's go ahead and get started. So obviously a research design is much more than a data analysis process. It's a research question, a theory, some information about the data that's going to be used and what level of analysis that data is going to be used at. A strategy to relate specific measures to concepts that are present in the theory, hypotheses, and so on. But we're going to talk about today, and for most of the rest of this class, is how to analyze data once these other steps are done. So for the most part, for the rest of the class, we'll be presuming all this other stuff where I will, in these examples at least, I'll give you, the research question, the theory, and so on. And we're going to be focused on how to actually analyze data once the rest of those the pieces of the research design process are already in place. So for today, for example, we're going to talk about how we can summarize information about a measure that we've collected. So for this particular example, we're going to use the Quality of Government Basic Data Set. This is an earlier version of the QUAG actually that I downloaded. It's not the most recent as of this recording. I believe it might be the 2015 version. It's also not the full Quality of Government data set. It's the basic data set. So the Quality of Government data set has lots and lots of information about countries over multiple years. The basic data set is just a snapshot of this data at one point in time and doesn't include the full range of variables. But one thing it does have going for it is it's relatively small. And so you can download it and get into R without waiting for a long time for R to load in some massive data set. Whereas for the full QUAG cross-sectional time series data set, it can actually take a fair amount of time just to load. So this data is at the country level, and it's a cross-section of those countries. The entire world, or at least the world for which we have data, for the year 2010. So that's the data we're going to work with. The first thing we need to do is get this data set open in R. So if you are following along the class at Wake and you have access to the RStudio server for the class, you already have this data available. If you change to the Paul 280 folder, so the first thing you have to do is change to the Paul 280 folder, you will see that if you scroll down here, right here, there's actually this one right here. This is the QUAG basic data set. You can see QUAG and then BAS for basic. That's the one we're going to be using today. And I actually have all of the commands that we're going to use today saved in a file for you. Again, if you're at Wake, and you have access to my RStudio server, you can just go in the Paul 280 folder, click on descriptivestats.r, and here it is right here. If you're not following along at Wake, if you're somewhere else, you can get both this code and the data set from my research website, or I'm sorry, from my teaching website. So the first thing we have to do is load the data. And actually, I'm going to change this file a little bit. I actually think it's better at this point to use the Haven dataset the Haven library rather than the foreign library. I think its compatibility with newer data is a little better. And so I'm actually going to save these changes so you'll see those changes in there. I'm going to use the Haven library and the read_DTA command in order to load the data. And of course, if I just run these things, I'm probably going to get an error because I'm in the wrong directory. This data is stored in the Paul 280 directory, and if I look at my current working directory, I'm not there. So if you're on the RStudio server, you need to set the working directory to the right location, and then these commands should work just fine. Of course, if you're doing this at home, not on my RStudio server in your own RStudio software instance, you need to set the working directory to wherever this particular data file is loaded. All right, so if we take a look at what's in this data set, and it takes just a second to load here, you can see there are 193 observations of 279 variables. Every observation is a country, so the first observation is Afghanistan. And if you scroll here, we've got all kinds of information about this country. And there is a quality of government code book you can see loaded on the server. Here's the code book for this data set, where you can figure out what all of these variables measure. But for this example, I'm going to pretty much just tell you what the variables mean. I'm going to pull the relevant instances out of the code book and just sort of talk to you about what those variables are. All right, so hopefully at this point you've got the data loaded, everything's ready to go. So now we can get started with some actual analysis. So the example problem we're going to look at right now is whether democracies grow more quickly than non-democracies. And by grow, I mean economic growth. Does their economy grow at a faster rate than does democracies' economy grow at a faster rate compared to a non-democracies? And to answer this question, we're going to look at two variables from the quality of government data set. The first one, WDI_GDPGR, is the annual percentage growth rate of GDP at market prices based on constant local currency. So essentially what we want to do is look at growth not accounting for inflation. So inflation is when prices go up just because the government or somebody, but usually the government, is printing more and more money, and there's more and more money chasing the same amount of goods. We're not interested in that. We're interested in real growth. In other words, the growth of essentially dollar-denominated goods holding prices constant, if that makes sense. Or not holding prices constant, but sort of holding the inflation rate constant would be the best way to do it. So inflation is going to be stripped out of this by using constant currency, essentially based on prices and the money supply in 2005. That's the sort of idea. This is measured by, I believe this is measured by the UN, if I recall correctly, although you can find out more about that in the code book. CHGA_demo is the Chebab, Gandhi, and Vreeland democracy measure. It's binary or categorical. It's coded 1 or 0, 1 for democracy, 0 otherwise. And in order to be a democracy, you have to have the executive and the legislature directly or indirectly elected by popular vote. Multiple parties have to be allowed. There has to be de facto existence of multiple parties outside of the regime front, multiple parties within the legislature, and no consolidation of incumbent advantage, which means essentially like changing term limits or somehow changing the Constitution to allow a certain party or a certain person to remain in power forever. So those are the two measures we're gonna use in our analysis, and we're essentially going to see whether countries coded as a 1, having democratic government, have a faster growth rate in this measure compared to countries coded 0. Just a quick note, there are lots and lots of ways of measuring democracy. This particular measure it involves a lot of different factors that all have to be true simultaneously. All are necessary, and they're considered jointly sufficient in order for a country to be a democracy. That's not the only way to measure democracy. You could measure democracy continuously. Let's say from -10 to 10 and every point in between. That's what the Polity Project does. But this conception of democracy is essentially, it's a little bit like the old joke about being pregnant. You can't be a little bit pregnant. And in this case, you can't be a little bit of a democracy. You are either a democracy or you're not. It's a categorical coding. All right, so let's look at these measures and see what the relationship is. Actually, I want to add one further note about this Chebab and Gandhi measure before we go to the analysis. So the paragraph I read you came from the Quality of Government Code Book, and I thought there was an additional characteristic, and I was right about this. So this is the Chebab, Gandhi, and Vreeland 2010 paper where this measure comes from, and you can see that you're coded as a democracy if Your chief executive is chosen by popular election or by a body that it was itself popularly elected. The legislature is popularly elected. There's more than one party competing in the elections, and this is the thing that I think was left out, an alternation in power under electoral rules identical to the ones that brought the incumbent to office must have taken place. And that fourth bit, you may notice, includes there has to have been an actual alternation in power. So you can't be a one-party regime even if you technically meet all the other requirements. If there's never actually been an alternation in power under the set of rules that were guiding elections, you're not a democracy, essentially. They're without real contestation. You're not a democracy according to this paper, or according to this measure. All right, now let's get to the analysis. Okay, so very basically, just to start, we could talk about the proportion of democracies in the sample. This is something you probably learned in grade school or middle school. Of course, you can do it in R2. So if we're asking just basically what proportion of the sample is democratic, that's the number of democracies over the total number of states in the sample, which is 1/100th the size of the percentage. And there are various ways of doing this in R, but the easiest way to do it is just to create a table and then look at the proportions of observations that are implied by that table. So if I go into RStudio here, you can see line 12 creates a command, or creates a table rather, called dem.table. It's a table, obviously, of the number of countries that are in each category of the democracy variable. So if I look at dem.table, for example, you'll see that 74 countries are coded as 0, which means non-democracy, and 118 countries are coded as 1, which means democracy. Those are the raw frequencies. Those are the raw numbers. If I then use prop.table to study that table, and actually I added in an additional dat there. It shouldn't belong there. You'll see that there are 61.5% of countries in this data set are democracies, and 38.5% are non-democracies. So, in short, what we have is the majority of countries in this data set are democracies. It's a very simple proportion. But of course, what we're really interested in is not just those simple proportions. We're interested in comparing the growth rates, or the existence of growth, perhaps, in democratic countries versus non-democratic countries. So what we need to do is create a table that has multiple rows and columns, where we can compare, for example, how many countries are in a state of growth among democracies compared to how many states are in a state of growth among non-democracies. So let's do that. All right, so what we really want to do is create a two-way frequency table and figure out if there are systematic differences between two groups, in this case, democracies and non-democracies. So what I'm going to do this is I'm going to create a variable that's essentially telling me whether a country is growing or not, growing economically. Recession is defined as typically, I believe, 2 quarters of consecutive negative GDP growth. Could be slightly wrong about that, but I think it has to be consecutive as well as 2 of them. We're going to define it more simply. We're just going to say if a country is ever experiencing a negative growth rate, it's in a recession in that year. So what you can see here, this code basically creates a new variable that has 2 values, recession or growth. And it's coded as recession if GDP growth rate is less than 0, and it's coded as growth if the GDP growth rate is greater than or equal to 0. So if I go into RStudio, you can see that same code is right here in line 15. Expand this out just a bit so you can see a bit more of it. So for example, if I just look at this inner command right here, what this is doing, this if-else command, and actually you can type $if-else to get a sense of what's going on here. This basically looks at a Boolean test condition, true or false. If this condition is true, it returns the first argument, or I guess the middle argument, the second argument. If the condition is false, it returns the second argument. So if in this data set, remember $$ variable, right? The $ separates the data set and the variable in that data set. If dat $WDI underscore GDP growth, if that value is less than 0, it is going to return a text string called recession. And if it's greater than or equal to 0, it's going to return a text string called growth. In other words, if this is false, if it's not less than 0, by logical exclusion, it has to be greater than or equal to 0. Okay, so that's what that inner part does. And then what this second part does is convert that text string into a factor variable. Now you'll notice this looks very much the same, but in this case they're in quotation marks, which indicates that they're string values or text values. In this case, they're not. They are actually factor labels. And so R internally sees this as factor bit as a, it sees it as an actual variable that can possibly take on numeric values, but it's a categorical variable, in this case with two categories. You can see levels, growth and recession, those correspond to the two categories. The first one will be coded internally as a 1, and the second one will be encoded internally as a 2. So if we want to make sure we've done this right, we could, for example, do a plot of WDI GDPGR against this new variable we created. Oh, I actually haven't created it yet. I have to store it in a argument called growth. Guess I'll go ahead and do that. And there's growth right there, factor with 2 levels. Then what I want to do is I want to plot this against growth. And you'll see I had to use the dat $ in order to tell it to look in the dat data set to find the GDP growth. But for the growth variable, which I just dumped into the memory space, I don't have to make that reference. Oh, interesting. It actually classified this as a category, and so it automatically created a box plot. So you can see it's cutting them off right at 0. So all the countries in the growth category have growths greater than 0. All the countries in the recession category have growths less than 0. Makes sense. And it's creating these categories because it's smart enough to know that growth is actually a factor variable. If I want to force it to make a scatter plot, I can convert growth into a numeric using as.numeric. And like I said, internally growth will be 1 and recession will be 2. And here we go. So when growth is 1, GDP growth is positive. When growth is 2, GDP growth is negative. Okay, so we have our variables. Now let's create our two-way frequency table. All right, so again, we're going to make a table, but we're going to make a table that has 2 variables: this growth variable that we created, and also the CHGA demo variable for democracy. And so if I create this grow table here, and if I look at if I just look at grow tab, again, I have numbers corresponding to raw frequencies. So there are 68 countries that are non-democracies and experiencing growth, 3 countries that are experiencing recession and are non-democracies, 97 countries are democracies and experiencing growth, 19 countries are democracies and experiencing recession. And just like before, I can change that into a table of proportions. But I have to add one bit of information. I need to tell it whether to create row proportions or column proportions. And I do that with this margin command. So let's say I run this command here, and I specify margin equals 2. So if you look at $prop.table, you can see margin is basically, this help file is not very helpful, but it tells you which direction to calculate the proportions in. So with margin equals 2, what I've done is I've calculated proportions via columns. So for example, in the non-democracies, 95% of those non-democracies, almost 96%, are experiencing growth, and only 4% are experiencing recession. Whereas among the democracies, 83, almost 84% are experiencing growth, and 16% are experiencing recession. So to go back to our original question, are democracies growing faster than non-democracies? Well, we at least know it's the case that democracies are less likely to be in a growth state compared to non-democracies. Sometimes I've gotten the question before: how do I label these things? This top margin, you can see the rows are labeled, the columns are unlabeled. If you want to do that, this actually pertains to how this CHGA demo is coded. You can see that in this case it is a labeled double variable, and I guess those labels are not getting carried through because it's not a factor variable. So if I wanted to, I believe I could just specify as factor and maybe this would work. I'm going to have to do a little bit more than that. I'm going to have to actually tell it I want a factor with labels of non-democracy for 0 and democracy for 1. And so what I did was, instead of using this raw CHGA demo variable, I actually changed that CHGA demo variable into a factor first with labels non-democracy and democracy, and then I put that into the table. So this actually illustrates how you can put commands sometimes inside of other commands in R. Like, I could have done it this way. I could have said, instead of doing this, I'm going to create a new variable called labeled democracy or something, I don't know, and then stored it there, and then said labeled CHGA instead, and that would have saying there's an oh, I forgot a parenthesis. And okay, there we go. That would have worked just fine. In other words, I create the new variable that has a label in it, I then label it in the table, and then I create the proportions, and then all of a sudden they're labeled. And I could even give this a better name if I wanted, something like democracy. Or maybe actually better would be govern type. Yeah, I like that. Regime type. Regime type. There we go. And now you get nice labels either way. But I can also skip that, and I can just take this right here and put it inside of there, and it'll still work, right? R will sequentially interpret the commands. But that enables me to have a nice labeled columns as well as rows. All right, so getting back to our question, democracies are less likely to be experiencing growth than non-democracies, but that is not exactly the same thing as saying that democracies do not grow as fast as, or grow faster, do not grow as fast as non-democracies, because it's possible that democracies do on average grow faster, but because the variation in how much they grow is so wide, they're also more likely to experience recessions compared to non-democracies. So to answer our question more accurately, we really need to do really need to compare something more like the average growth rate between the two states. So let's talk about means and standard deviations, and that will enable us to assess whether the growth rate inside of democracies is faster or slower compared to non-democracies. All right, so again, something that most people see in grade school or middle school, maybe high school, is the mean, or also known as the average. The mean is a measure of the center of a distribution of observations. So, for example, if we were asking the question, if we randomly picked a country out of the democracies, what would be our best guess about its growth rate? The average or mean of democratic growth rates would be our best guess. That would be the guess that would be, by some measures, the closest to the right answer. You can actually change that a little bit by depending on how you define closeness. So the mean, in case you need reminding, is just add up you calculate a mean by adding up all the values of the target variable, and then divide by the number of observations you have. So that's this formula right here. R will, of course, do this by asking for the mean. You do have to specify in R that you want to remove any missing values, because the average of 2, 3, and 4 is obviously 3, but the average of 2, 3, and question mark is unknown. It depends on what question mark is, right? If question mark is 5 million, that's going to be a different mean than if question mark is 3, right? So you have to tell R to explicitly drop those missing values to calculate a mean if you want to do that. And then, of course, we can calculate the means for democracies and dictatorships separately, non-democracies or dictatorships, and then we can see whether their growth rates are different. So going back into RStudio here, where am I here? Okay, so this is a simple mean of all of the GDP growth rates in the entire sample of countries, both democracies and non-democracies. The average growth rate in the sample is about 4%, just a little over 4%. I'm going to skip these things for a second and go down to calculate the mean growth rate. Oh, actually, I guess we have to add this in. So we need to calculate the growth rate for these countries separately according to whether they're democracies or non-democracies. And so what I can do is I can go in and say I want the mean. Oops. I only want certain observations. I'm going to use the brackets to specify which observations I want. We learned earlier the bracket enables us to basically choose certain observations. So if I wanted the mean of the first 10 observations, I could do 1 through 10. But I don't want the first 10. I want all the democracies. And so what I want is the observations for which CHGA demo is equal to that label. So if you look at what values, CHGA demo can take on, it's a 0 or a 1. 0 is dictatorship, 1 is democracy. So if I look at this, if I just type this part in, I guess, that's because of the way, it's a difference in the way if the foreign library and the foreign library and the Haven library load things. So actually we can be a little simpler here. If I want all the democracies, I just need to say the value is 1. There we go. So if I look at this, there we go. The trues are the observations for which CHGA underscore demo is 1. The falses are the ones for which it's not equal to 1. It's either missing, like here, or it's false, which means it's a dictatorship or a non-democracy. And so if I look at this vector without the brackets, I get a vector of length 193 because there are 193 countries. But if I look at with the brackets appended to that variable, I get a vector only of length 13, 14, 15, 16, 17, 18, 119 because there are 119 democracies in this data set. So if I look at the mean of those 119 observations, I get 3.24% growth per year on average. And then if I do the exact same thing, but I say I want the non-democracies, the mean is 5.5%, considerably higher. So it seems like democracies on average grow more slowly than non-democracies according to their growth rate. And we can get an even better look at this if we do a histogram. So I'm going to actually jump down here. Look at this right here. This is line number 36. So this is a histogram of growth rates among democracies. And then I can repeat this for non-democracies. Oh, here's all this code down here. I've already done all this. I'm just reinventing the wheel. So if I go down here, I need to change this code a little bit because the Haven and the Haven and foreign libraries treat these a little differently. So I'm going to train this to 0. I'm going to change this to 1. I'm going to save those changes so that you see those on your basic file. Okay, so here we go. If I do a histogram of growth rates among democracies, I get this. And you actually notice I set breaks equals to 10 to get a little bit more granularity in the histogram, more bins. I can compare that to dictatorships right here. That's the distribution of growth rates among dictatorships. And if I really want to, I can show them both at once by setting this graphics parameter here. So mfcall equals c2, 1. This tells R to create a plotting space that has 2 rows and 1 column, and then it'll sequentially fill those spaces with the next plot you make. So if I set this, it appears that nothing happens. But when I next run the dictatorships thing, you can see it puts that dictatorship graph right in the top. And then if I do this for democracies, it puts that in the bottom. And that makes it a little easier to sort of eyeball what's going on here. And it'd be better if I put them on the same scale, wouldn't it? So if I come in here and I say, I want xlim to be between -10 and let's say 20 for both of them. So let's try this again. There we go. xlim c equals c -10, 20. Bam. Now they're on the exact same scale. And what you can see is the dictatorship growth rate is higher, right? The entire histogram for democracies looks like it's been shifted to the right. So it is possible, it's theoretically possible to have a higher mean growth rate, but also be more likely to be in recession. So if democracies had a really high mean growth rate, but were widely dispersed, it would be possible for that more democracies were in recession, but the mean growth rate was higher. But in this case, we can see from our histogram, and we can see from our mean calculations, which you did before, they're right here, we can see that that isn't true. You can see that, in fact, they're basically have the same degree of dispersion, and it's just that the dictatorship growth rate is shifted higher. So now we have a bit of a better answer to our original question: do democracies grow faster than dictatorships? And at least in this sample, the answer seems to be no. In fact, dictatorships do on average grow faster. Now, I just want to put in a caution that I would always add. Be careful of interpreting this to mean that dictatorships cause faster growth. There are lots of possible confounding factors, things that can cause both regime type and growth. For example, GDP level. So are you a rich country or a poor country? Rich countries tend to grow more slowly. Rich countries, because they just have more stuff, so it's harder to grow more. It's really easy to grow fast if you don't have much, right? Because if your country is nothing but rubble, if you put one brick on top of another, that's 100% growth. Whereas if you have lots and lots of stuff, it's hard to continually, because you have to replace your capital stock. It's hard to grow even faster because basically things wear out and have to be replaced. And so once you have a lot of stuff, you're just replacing stuff that's wearing out. Kind of went down a hole there, rabbit hole. Anyway, rich countries have trouble growing as fast as poor countries. And so it's possible, again, this isn't necessarily true either, but it's possible that there's a confounding factor here in wealth, right, in GDP level as opposed to GDP growth. It's also possible that there's reverse causality. It's possible that faster growth somehow causes a country to be more likely to be in dictatorship. Not sure why that would be the case, but something we would need to consider. So we answered our question. At least in this sample, democracies do not grow quicker than dictatorships. I'm just saying, be a little careful before you jump to the conclusion, oh, that means dictatorships cause faster growth. It might be true, but we'd have to do a lot more work before we could decide that. All right, so now what I want to move on to talking about is dispersion. We already hinted about this when we were talking about the histograms. That was a sort of a factor we thought might be important. Let's talk a little bit more about dispersion and talk about some specific measures for that. All right, before we talk about variation, I just want to mention I did change the slides here to reflect, first of all, the different way that Haven reads in the CHGA demo variable. So instead of reading it as a factor, it reads in as a number. So I changed it to that. I also added these $$ prefixes because it might be a little unclear in the slides that you need to, if you don't, basically have to reference the data set where the variables come from in order for them to work. And so even though I had that in the R file, I thought it'd be nice to put that in the slides too. So the previous slides have been updated to have that, and they have this updated coding. All right, let's talk about variation. So when we were just talking about democracies and growth rates, we mentioned that if democracies experience wider variation in growth rates, it might be possible for them to be more likely to be in recession and simultaneously have a higher growth rate. So that's one reason among many why you might want to ask how much variation there is in your data. Variation is essentially to what extent are the observations in your data set different from one another. So for example, if we're measuring height, to what extent we can calculate an average of height, right? The average height might be 5'9" or something. But you can have a data set where everyone's 5'9" and the average is 5'9". You can have a data set where there's wide variation from person to person and the average is 5'9". 5 foot 9 inches. for those of you who are in metric countries, that is to say everywhere but the US. Anyway, so this is something that's often of interest to an analyst, and it's something we can certainly take a look at. So we did look at the GDP growth rate for democracies and non-democracies just a second ago using a histogram. Histograms are one very good way to assess variation. We've already done that. We could also use box plots, which have a measure of variation embedded in them. We've already talked about box plots previously. The interquartile range is a measure of variation that's embedded in a box plot. So to know what an interquartile range is, we have to first talk about percentiles. So a percentile is a value of a variable for which some proportion of the data is smaller than that value. So the 50th percentile is, for example, for the 50th percentile of GDP growth rate would be the value of GDP growth for which 50% of the data is smaller than that value. The 25th percentile would be the value of GDP growth such that 25% of the data growth rate in the data is smaller than that value. So in this teeny weeny data set we have as an example here, 7, 8, 9, 10, 11, 5 observations. I don't know what that number would be, but it's a number. The median, or the 50th percentile, would be 9 because half the data is smaller than 9, half the data is bigger than 9. Since 9 is literally the middle number, we sort of count it on both ends. So it's, it is the observation for which half the data is smaller than it. The 25th percentile here would be 7.5. So you can see we need 25% of the data to be smaller than some number. There are 1, 2, 3, 4, 5 observations. 25% of 5 is not an even number, right? So if you go back to RStudio here, 25% of 5 means 1 1/4 observations should be smaller than that number. There are several ways to sort of calculate this, but one easy way is to just put it in between those two numbers. So if one value has to be smaller than it, right, it's just between 1 and a quarter. You can't have a quarter of a number. So we'll just say the 25th percentile is 7 because one number is smaller than it. That's how it would work in that case. So once you know what a percentile is, you can then talk about an interquartile range. An interquartile range is the distance from the 25th percentile of the data to the 75th percentile of the data. And it essentially tells you how far apart the two sort of, not endpoints, but sort of midway between the ends, so to speak, how far apart those 2 points are in a data set. So if we go back to RStudio here and look at this, you can see I've calculated you can calculate percentiles for GDP growth, and actually here we're looking at 2 different percentiles for GDP growth, one for democracies and one for non-democracies. This is the non-democracy here, this is the democracy right here. For the moment, I'm just going to look at the entire data set as a whole. And so the quantile function returns percentiles. You give it a variable as the first argument for which you wish to get the quantiles. So if I look at help quantiles, there we go. You can take a look at this help file. The first argument is the variable for which you want the quantiles. The second argument is probs here, is what quantiles you want. And then this argument NA remove just tells it to drop missing variables, or drop missing values rather, from the variable. So I'm telling it I want quantiles of GDP growth, or percentiles. Quantile and percentile are synonymous. I want the 25th percentile, the 50th percentile, and the 75th percentile. And I want to drop the missing values. And so when I type that into R, I get this answer. The 25th percentile growth rate is 1.72. That means 25% of the observations in the data have growth rates smaller than 1.72. The median, or 50th percentile, is 3.98, so almost 4. So roughly half of countries have growth rates in this data set smaller than 4%. And the 75th percentile, or quantile, is 7. Actually, it's exactly 7, which means 75% of countries have growth rates that are smaller than 7%. So if I were to construct a box plot of this, so if I just do, by the way, if I just do a box plot, it's still in the mode of putting the 2 plots next to each other. So I have to restore that to its original value by using par mfcall and then setting it to 1, 1. So basically it's one plot. And then I do the GDP growth rate. Now it'll do it sort of the full thing. You can see here's the median. Going back to the quantile, we said the median was about 4. Here's the median right here. It's about 4. 25th percentile is 1.72. There's 1.72. The 75th percentile is 7. It's right there. And then the interquartile range is the gap between this value and this value. So in essence, what we have here is the 25th percentile, the interquartile range, is the distance from the 25th percentile to the 75th percentile. And the bigger that box is in the box plot, the more variation there is in the data. So you can see the minimum and the maximum excluding these outliers, and we'll talk about what outliers are in a second. The minimum and the maximum excluding these outliers is pretty spread out, but most of the data, I would say exactly 50% of the data, is located in between these 2 bars, and that's the middle 50% of the data, right? From the 25th percentile to the 75th percentile is the middle 50% of the data. And this gives us some sense of how dispersed the data is by looking at sort of how spread out the middle 50% of the data is. And in this case, what we see is most countries in this data set have growth rates that are crowded around, that are basically clustered around 4%. A little higher, maybe 6 or 7%, or a little lower, maybe 1 or 2% is possible. But most of the countries have growth that are somewhere in that range. And of course, I've added this here. You can do 2 box plots for democracies and non-democracies separately. And this gives us the conclusion we got before, which is that the non-democracies tend to have higher median growth than democracies. And moreover, their interquartile ranges are actually fairly similar. So there's not a big difference in the dispersion of growth rates between democracies and non-democracies. All right, so this just says what we already did. You can depict variation with a box plot. The box plot shows the 25th, 50th, and 75th percentiles. It also shows the range of the data that are not outliers. So that's the sort of minimum and the maximum of the data. Like so, going back to this, the minimum and the maximum of the data that don't count as outliers. And then finally, it shows you the outliers. And so an outlier is classified as any observation that is more than 1.5 times the interquartile range away from the 25th or the 75th percentile. So going back to R here, there we go. This data point right here is more than 1.5 IQRs away from this edge of the box. And so it gets classified not as the maximum, but as an outlier. These two observations here are more than 1.5 times the IQR, 1.5 times the width of this box away from the 25th percentile, so they're classified as outliers. These are essentially observations that are very, very far from the center of the data, and ergo they get classified as sort of not being representative of the distribution of the data in some sense, if that makes sense. So box plots are one way of depicting, there we go, variation in the data. This is a funny little cartoon from XKCD, which is a great cartoon if you like statistics or science or social science or math. So the comic, I'm going to ruin this joke by explaining it. The comic says, "Oh, can my boyfriend come along?" And then the guy denies being the woman's boyfriend. And then she says, "I can prove it with statistical analysis." And she produces a box plot and shows him that he is an outlier in the box plot. So he spends more than 1.5 times the IQR greater than the 75th percentile of people she spends time with away from everyone else. And then she claims that he is her statistically significant other. So having completely ruined that joke, I will now move on. Oh, there we go. Box plots and IQRs are not the only way of depicting variation, obviously. Variance is probably something you've heard of if you've taken a previous statistics course. And in the event that you know every possible case in the population that you're studying, and in this case, it's arguable. We do have maybe every country in the world, but we don't necessarily have every possible realization of every country in the world over time. But if you do have every possible case in your target population, the variance is just, it's like a mean in a sense, but instead of computing, adding up all the y's and then divide by n, you add up all the gaps or differences between y and its mean, and then square it, and then divide that by n. And essentially it is the average squared distance from an observation to its mean. One thing that the squaring does is it puts negative and positive differences on the same scale, because a negative difference squared becomes a positive difference. It also tends to give greater weight to bigger differences. So as anyone who's been in Algebra 2 and seen a parabola knows, when you depict x against x squared, as x gets bigger, x squared gets geometrically bigger much faster. The same thing is happening with the variance here. As this gap between y and its mean gets bigger, the variance contribution gets larger. So it's an average squared distance. And then for reasons we don't really go into in this class, if you have a sample, you actually need to estimate the variance in a slightly different way. So if you have a sample of a population, you're estimating the population variance with the sample, and just computing the average squared distance in the sample will actually slightly underestimate the population variance. And so instead of dividing by n, you do the same thing in the sample, but you divide by n minus 1, which slightly inflates the variance estimate in the sample and gives an unbiased estimate of the population variance. So we're estimating the population variance using a sample. We'll talk a little bit more about population sample differences later. But for now, it suffices to know that if you have a sample, you divide by n minus 1 instead of n. And of course, you can take the square root of the variance to get the standard deviation. And the standard deviation is just, in essence, the average, well, not quite. It's a measure. It is a measure of the distance between y and its mean, but it's not exactly the average distance because you're taking the square root not just of the numerator but also of the denominator. So it's not exactly the average distance. But its standard deviation is the square root of the variance. R will obviously do these things, and so I need to add in the DAT modifiers here. But var and SD calculate variance and standard deviation respectively. And so going back to RStudio, and actually I think I have this up here. If you want to calculate the standard deviation of GDP growth around the world, SD will give you the standard deviation, and var will give you the variance. And just so you know, when R makes these calculations, it's going to treat these. It's going to treat the data as a sample, and so it's going to divide by n minus 1 when it calculates the variance, for example. And you can learn more about these. Commands in R using the question mark. It explains exactly how it makes its calculations and various things you can set, and so on. Okay. Well, that's it for that bit. So other than the interpretations that I've already given, there is a situation in which variance has a more meaningful interpretation, and that occurs whenever a variable is distributed normally. So we're going to learn more about the normal distribution later, but for right now, you've probably seen something like this. This is a picture of a normally distributed variable. Normal distributions have this bell curve kind of shape, and you can see what I've depicted is some variable distributed around a mean of mu, and having a standard deviation of sigma. And if a variable is normally distributed, then 68.2% of the observations in the population are within one standard deviation in either direction of the mean. And then within 2 standard deviations of the mean, let's see if I can do this in my head. 68.2 plus, what is this, 27, oh, I hate doing head math. Screw it, we got R. 68.2 plus 27.2. Yes, 95.4% of observations. I knew it was about 95, but I didn't know what the decimal was. About 95% of observations are within 2 standard deviations of the mean. And then about 99% of observations are within 3 standard deviations of the mean. So in the case that a variable is distributed normally, this variance tells you something kind of akin and actually a little more specific than the interquartile range. It actually tells you exactly how much of the data, or where the data are going to be concentrated, right? How much of the data is going to be in what locations. So if I should actually explain, I just took this for granted and should explain this more carefully. This distribution here, this bell curve, this is a frequency distribution, and it's a bit like a histogram where the bars are infinitely thin. And so, for example, right here at the mean, a value is most likely to occur in this distribution, and then further out, as you go more and more standard deviations away from the mean, a value is less and less likely to occur. And if a variable is normally distributed, what we know is that 99% of its observations from this population are going to be within plus or minus 3 standard deviations of the mean. Now you may be thinking, that's great, but how often are variables normally distributed? It turns out that there are some special cases where we can prove, we can guarantee that something will be normally distributed. And those things that will be normally distributed are important for the study of statistics. And so although right now it might be hard to believe that, for example, GDP growth is normally distributed, maybe it's not, maybe it is. From those histograms we saw, it's kind of normal-ish, but maybe not exactly normal. Still, there are going to be some very important quantities that are normally distributed, and that's where this variance identity is going to come in handy. So keep it in mind for now, file it in the back of your head, and it's going to come back again later. Obviously, not all variables are normally distributed. In fact, many variables are not normally distributed. I'm going to give you some examples of distributions that are not normal. This is a uniform distribution. So just like before, like here, this is like a histogram, right? In this case, you can actually see the literal bars in the histogram. So here we sort of assume that the bars are really, really thin. Here you can actually see the bars. And what a uniform distribution is a distribution that puts equal probability on all values in some sort of range. So for example, here, in the normal distribution, the most likely value to occur is the mean. But in a uniform distribution, in this case, every value between 0 and 1 is equally likely to occur. Now, 2 will not occur at all, and negative 2, this is past 0, will not occur at all. But anything between 0 and 1 is equally likely to occur. And obviously, this variance identity would not hold in the case where a variable is uniformly distributed. Here's another. This is actually data I took from Wikipedia. I believe this is data on the distribution of ant, as in the little insect, ant body lengths. This is a bimodal distribution, which means there are two modes. The mode is the most frequently occurring value. In this case, we have two most frequently occurring values. This one occurs slightly less often than this one, but they're still sort of obviously competing modes. Probably because there's a worker ant population and a warrior ant population or something, who knows. I'm not an entomologist. but again, clearly not a normal distribution. We wouldn't expect this identity to hold in the case of a bimodal distribution. Some variables are going to be distributed that way, and in this case, we couldn't apply the variance identity. All right, so just to take a little side detour here, we were talking earlier about political freedom and the relationship between political freedom and growth. We could think about economic freedom and growth. There might be more of a relationship between economic freedom and growth than political freedom. Economic freedom and political freedom are not the same thing. So I've got this score from the Heritage Foundation in the Quality of Government data set, the Heritage Foundation Economic Freedom Index. It varies from 0 to 1. 100 is the highest possible value of economic freedom in the data set. And what we want to do eventually with this is see maybe if economic freedom is associated with GDP per capita, or maybe even GDP per capita growth, using a box and whisker plot. But before we do that, we need to create categories of economic freedom so that we can create different boxes for our box plot. So again, we're creating a variable, a categorical variable from a binary variable like we did before. What we're going to do is classify any country that has a economic freedom score of 60, or actually greater than 60, as being free. Any country that has a score of 60 or less is going to be categorized as not free. And you can see we're creating this factor variable like that, same way we did before. So if I go into my RStudio here, you can see I have this all prepared for you already. Here's actually a raw scatter plot before we get started. Let me shrink this down so it's a little easier to see. This is a raw scatter plot of the relationship between economic freedom and this is GDP growth, right? This is growth rate again. And actually, if I were just to eyeball this, I would say there's probably a negative relationship between economic freedom and growth. I'd say probably something like, there's a line that goes through it, something like that. In fact, if you really want to, I can add that line. There we go. In fact, there does appear to be a negative relationship here, which is kind of interesting in its own right. If I wanted to compare a group of free countries that have high scores with a group of unfree countries that have low scores, I could use the if-else command again to create this free variable. And you can see if I plot the free variable against the if-I score, now all the free countries have scores above 60. All the unfree countries have scores less than or equal to 60. And I can make the free variable have a nice label using the factor command. In fact, I don't need to have asFactor in here. I can just take that out. This will work just fine. In other words, that was redundant. So now if I type free here, you can see I have countries with nice little labels of free and not free. And then I can create a box plot of GDP growth against not free countries and free countries according to the Heritage Foundation. And as you can see, economically unfree countries tend to have higher growth rates compared to economically free countries. And I can create a pair of histograms just like I did before. There we go. I've even put them on the same x-limit axis here. That's nice. And you can see excuse me, the difference between free and unfree countries doesn't seem to be quite as stark as the difference between politically free and unfree countries in terms of GDP growth. But there's still a difference there. So sometimes the variance itself is a substantively interesting quantity. For example, if we're thinking about polarization, or saying in a slightly different way, variation among ideologies in congressmen, we could sort of study the variance of congressional ideology over the last 100 years and see if the average distance between congressmen in terms of their ideology has changed in that time. Now, polarization sometimes means, people sort of clustering at two poles, and that will be picked up as a higher variance, although there are other ways that could happen too. You could simply get a sort of a normal distribution that was more and more and more spread out. And we could possibly look at both of those things. But as a crude first sort of cut at this, we could say, well, let's study the variance of congressional ideologies just sort of on its own and see if we can see if that variance has gone up over time, if the average squared distance between congressmen and the mean ideology has gone up. Actually, I'm going to change this again to be the Haven library, because I think this is a little better than the foreign library. So if I load in this data set here is basically a measure of congressional ideology as captured by DW nominate scores. DW nominate scores are a little hard to explain in briefly, but essentially what they are is measures of ideology that come from congressional voting patterns. You use the way that congressmen vote to classify them according to their ideology, and then you get a score from that you can then look at and use as a metric of a congressman's ideological position. So I've loaded into you can see in the environment here, we've got this ideology score now, and we've got lots of observations of 16 variables. And one of those variables, if you click here, is the Congress. So the first Congress was literally, Congress number 1 was the first Congress that was convened after the signing of the Constitution. We don't want to go back that far. We're just going to start at Congress number 60. So I'm going to subset the data to only have Congresses starting with the 68th Congress. And then I can create a box plot. So what I'm doing here is I'm creating a box plot where the Congress, all the way up to, looks like the 111th Congress, maybe the 112th, is plotted. So this is the 60th Congress, the 61st, the 62nd, and so on. And the ideologies of the congressmen are in each Congress are plotted over time. And you can see the median kind of moves around. It shifts as different parties take control, the Democratic or the Republican Party, as they take control of the chamber, the median shifts from one to another. But what we're really interested in here is the size of the interquartile range box growing, right? So the two parties getting further and further apart, such that the congressman with the 25th percentile ideology is further and further apart from the congressman with the 75th percentile ideology, which in the U.S. Congress, which is a two-party system, that probably means someone roughly in the middle of the Republicans. How do they compare to someone who's roughly in the middle of the Democrats? Is that getting bigger and bigger? And in fact, just sort of eyeballing this, you can see there's a little bit of a collapse here and then an expansion. So it sort of comes in a bit and then it starts going out and out and out and out again. Well, what we could do is we could create, we could measure the standard deviation of ideology in every Congress from the 60th to the last one, the 102nd looks like is the last one, and then plot that directly. So what I've done here is I've set up a little loop, and here's how this works. So the first line, 105 here, creates an empty measure. So ideology.sd is a vector with nothing in it. It's null, returns null. And so what I'm going to do is I'm going to step through every single Congress. So for I in 1 to 112, this is called a for loop. And what it's going to do is it's going to do whatever's in between these brackets, inside of the for loop. It's going to start with I equals 1, and it's going to do this thing. And then once it's done, it's going to move I up by another increment, and then it's going to do it over again. So when I equals 1, it's going to set the first element of the ideology SD equal to the standard deviation of DW nominate score for the Congress that is equal to I, which is really the first Congress, the second Congress, the third Congress, and so on, right? So it's basically going to subset every Congress, calculate the standard deviation of ideology according to DW nominate score in that Congress, and then it's going to move on to the next Congress, right? So if I just run this loop, this will happen in a matter of seconds. It's already done. Then what I can do is I can plot the standard deviation of ideology over time. And so if I start with the 40th Congress to the 102nd, so here is Congress.plot. This is just a measure here of what Congress we're in from 40 to 112. And then ideology standard deviation is on the y-axis here. This is the measure we just created with the for loop. And what you can see is starting with the 40th Congress, there seems to be a gradual increase in the gap, right, between the 20, the gap between the mean and the standard deviation is the square root of the average gap, squared gap between the mean and an observation, right? So that gap gets bigger at first, then there's a big collapse and it gets a lot smaller, and then it starts gradually getting bigger again until we arrive closer to the present day, and the gap is very, very large, right? So this is a case where we're specifically interested in the concept of, are congressmen sort of further apart from each other than they used to be? Is the gap bigger? We measure that gap directly with standard deviation, which is just the square root of variance, and then we measure it in each Congress using this ideology measure we've come up with. And you can see, in fact, it has changed over time. This is actually during the World War II Great Depression period. There was an increase in polarization, a sudden collapse after the Great Depression and World War II, and then it starts creeping up again, and now it's higher than it's ever been. So this is a case where variance or standard deviation is actually the quantity we're really interested in, and sort of it's interesting in its own right. So there's one more thing I want to say about outliers before we end this lecture. The presence of outliers in a data set can make measures of central tendency like a mean very misleading. So for example, suppose there are 3 people sitting in a bar, 2 ordinary sort of workers, and Bill Gates. If you were to average their salaries, you would get a very, very high average. I guess, I don't know if Bill Gates makes a salary anymore. If you were to average their wealth, you would get a very, very high value. But that would not be a very good indication of sort of what the middle person, what the average person in that group makes. In fact, even if you were to have 20 or 30 people sitting at a bar, and Bill Gates was one of them, and everyone else was just an ordinary person, the mean would be dragged way up relative to the true center of the income or wealth distribution in that group. And you can see this in R. So I have a little example prepared. It's right here. So what I'm doing here is I'm clearing out everything we just did before, and I'm setting the seed of the random number generator to 1, 2, 3, 4, 5, 6. This just ensures that you and I, if we run this code in the exact same order, we'll get the exact same answer. And then what I'm going to do is I'm going to draw 10,000 observations from the uniform distribution between 0 and 100,000. So we mentioned the uniform distribution before. If I did a histogram of this fake income variable that I just created, it looks uniform. Everyone has a roughly equal chance of making between $0 and $100,000 in this data set, with a little bit of variation just because you draw lucky or unlucky samples depending on exactly who you're looking at. Now let's suppose I draw one person in this data set to have a huge income, 1 times 10 to the 9th, which is far larger than anyone else in this data set. So if I don't have that person in the data set, I would expect to get a mean of about 50,000, which is roughly in the center of, it's exactly in the center of the theoretical distribution between 0 and 100,000. But if I add this person, so if I say the first person now has to make 1 times 10 to the 9th many dollars. That's a 1 with, was it 9 zeros in front of it? So that a very, very large number. Now if I take the mean of fake income, I get an average income of $149,000. Now you'll notice, looking at this fake income distribution before I added the really rich person, $150,000 wasn't even a possible value, right? There's no way that $150,000 is near the center. And in fact, if I were to go back and make a new histogram, you'd see that everyone is basically here except for this one person, right? So over here is not the middle. The middle is still where it was, right? It's still roughly in here somewhere. So the presence of outliers can really make things confusing when it comes time to sort of measure a central tendency. So there are responses we can do for this. One is to simply drop outliers. And one way of doing this is to calculate a trimmed mean. So you basically take everyone in the data set or every observation in the sample, you line them up from smallest to largest, and then you drop the first 2 and the last 2, or the first 1 and the last 1. And the mean command in R has a trim command built in, so you can trim things sort of automatically if you want. And you can see right here, if I tell it to trim the biggest and the smallest observation in this group, now I get a mean of 50,000, which is closer to what the actual middle really is. Another thing you could do is you could take the median. So the 50th percentile doesn't change very much when you add a big or a really small observation to the end, because the middle is still pretty much the middle. And so medians tend to be more resistant to outliers than means. And so you could sort of check to see whether the mean and the median are substantially different from one another as a way of seeing whether an outlier may be dragging things around. And then finally, what you can do is try to find them and identify them and maybe explain them as sort of anomalous observations and drop them before you calculate means or other measures of central tendency. And this is important not just because there are these sort of anomalous cases like Bill Gates, who just has way more money than most people, but also sometimes outliers are not real observations. They're data entry errors. right? Someone accidentally types more zeros than there should be, and suddenly you've got a person making way, way more than they should. So, for example, if I wanted to identify which observations had really, really large incomes, I could use this which command, and it just tells me literally which observations, which indexes in the fake income index have, let's say in this case, fake income bigger than a certain value. It's bigger than 100,000. And it tells me only one of them does. So if I were to change this to something like 99,000, I would get quite a few people have incomes bigger than 99,000 in this data set. But there's only one person that has an income that's bigger than 100,000. It's that first guy that I added. And then you can use this fake income thing to identify those outliers. So if I store which people have the income bigger than that as an index, I've stored that in something called outliers. So outlier, whoops, out now has it's 1. And if I look at, if I use the brackets to index which observations I'm looking at, I can see, oh, there's this one person that has a lot of money. And if I were to change this back to, so before I did something like 99,000, if I redefine my outliers differently, you'll see then I'd get more people here. And you could very clearly see, oh, all these people are sort of in the same ballpark. They're in the 99,000 ballpark, essentially. And then there's this one guy with $1 zillion, right? Is it 1 times 10 to the 9? Is that actually 10 billion? 100 billion? Yeah. 1 times... it is a 1 with 9 zeros after it. 1 with 9 zeros would be 1 billion, I think. 1 times 10 is 6, whatever. Anyway, so the moral of this particular observation, or the moral of this particular demonstration is measures of central tendency can be misleading if there are outliers present in the data, and it's probably a good idea if, particularly if you do a box plot or a histogram and you see some observations are way off, to identify them, to check to see whether they are really observations. If they're not, get rid of them. If they are and they don't really fit in with the rest of the distribution, you might consider getting rid of them, although you wouldn't certainly want to ignore them. You'd want to say this is a mean excluding these outliers. And essentially you shouldn't just type mean and then a variable and then return and whatever comes up, well, that must be the answer, right? You want to think about the fact that there might be outliers influencing that answer. All right, that's it for basic descriptive statistics. Next time we'll talk more about probability distributions, which you may remember this is a probability distribution, and we're going to talk more about what this means and how this works. And that'll be in the next course video. So see you then.